So I'm Tom Talpey from Microsoft. I'm an architect in our file server team, which is to say I'm in the Windows Server, or now called Cloud and Enterprise division. I've been there for about 5.5, almost 6 years. In a previous life, I attended a number of OFA workshops talking about NFS RDMA and some of the RDMA requirements that NFS RDMA would like. So I've come here with several different hats on, and I'm coming here today with a couple of different Microsoft hats on. I'm basically going to give, when I have a slide, I'm going to give some overview of the breadth of RDMA interest within Microsoft and some of its products and services. I represent at Microsoft the SMB file server. I'm an author, co-author of the SMB3 and SMB Direct, which is the RDMA binding of SMB. But it goes far beyond SMB Direct at Microsoft, and there are a number of other groups using RDMA, which I will introduce a little bit. Find it?
Yeah.
Thanks. Sorry. No problem. Okay, here we are. Introduction. So it's a highlights presentation, okay? I'm not going to drill down on any of these things, but I'm just going to try to spread a broad brush across a few areas of the company. And first, I'm going to start off with SMB3, SMB Direct. I'm going to move to Windows networking. There's actually two sections to this, one in the middle and one at the end. Windows Azure, which is deploying RDMA, or in the process of deploying RDMA. And a few interesting things about software interfaces. I think you'll be interested in those from a programming standpoint. So first, SMB3 and SMB Direct. A little bit of an eye chart, I apologize. SMB3 is the primary Windows remote file protocol. It has this long history way back to the 1980s. It was called CIFS, then it was called SMB1, then it was called SMB2. The current sort of benchmark version of SMB is we call SMB3, Dialect 3. There are two shipped versions of SMB3, one in Windows Server 2012, also Windows 8, and it upped to SMB 3.02 in 8.1 and Windows Server 2012 R2. We are currently previewing SMB 3.1.1, that's the number of the dialect. The differences between all these three things are pretty technical. There's some slides in the backup that'll help navigate that. But basically, SMB3 has enterprise application features. It has a specific feature called continuous availability to support high availability of applications. It supports the full Windows File API, enterprise applications. In particular, it's fully supported by Hyper-V and SQL Server for their storage features. And it's also used by Hyper-V for live migration, and that's where an interesting scenario for RDMA comes in. So it's a transport layer adapting SMB3 to RDMA. I'm telling you this because I love it. It's fabric agnostic. IWARP, InfiniBand, and ROCE, all three are supported in-box in Windows. It uses IP addressing. It has an IANA standard port 5445. We make minimal RDMA provider requirements, so it enables the greatest compatibility for current and future adoption. We only use send, receive, RDMA read, and RDMA write. We don't use atomics, immediate data. We only use RC. It's just really basic, right down the plate kind of a requirement set. And we support IWARP on the former Intel NetEffect 020. That's actually obsolete in 2012 R2, but was supported in 2012. All the Chelsea OR NICs, the T400 series and 500 series. For ROCE, Mellanox HCAs at both 10 and 40 gigabits, depending on the generation. And InfiniBand, Mellanox HCAs, similar generations and hardware, all the way up to FDR in the current product. And all these things will continue to track the vendors' point of the spear offering, shall I say. So there are two really interesting features of SMB3 Multichannel, or SMB3. The first is multi-channel. Multi-channel allows a client and server to connect in a trunked fashion. And the laser pointer is kind of mild, but it can connect anywhere from 2 to 4 times, actually an arbitrary number of times, but by default 2 to 4. And in particular, it can connect with dissimilar types of transport, including RDMA. So we use multi-channel to both support failover and bandwidth. It's basically both a teaming and an availability feature. And it's used to detect and use multiple paths, including detecting RDMA. And when it does detect RDMA, it shifts into this thing called SMB Direct. It's scalable, fast, and efficient storage access. You've seen all this. Actually, I think I used a slide very much like this at last year's panel presentation, which was just a quick one. But it's basically full SMB over an RNIC using the SMB Direct protocol. There's some links in the backup to help you with that. Required hardware is only an RNIC. It's basically plug and play. When you install the RNIC, the client and server discover their capabilities and start to try to use them. So SMB is SMB, particularly with SMB Direct, but this is true of any SMB. It has a few key file I/O workloads. It's file I/O. The first is small and random workloads. 4 KB to 8 KB is what we define it. They're always, always, always IOPS sensitive. They're very rarely bandwidth sensitive. They require low CPU, but in particular, they all look for high IOPS. And they're used it sounds like a tuba or a trombone. They're used a lot for databases. They're used a lot for file systems. So you see them in SQL Server and Hyper-V workloads. Very, very common workload for modern SMB because of the application target. They're also used for large and sequential, 512 KB and up. Those are universally bandwidth sensitive. Nobody cares about IOPS because there's basically a few thousand IOPS to max out the wire. But large sequential is the other common storage workload. And there are smaller workloads, and they're also larger. SMB typically will transfer up to 8 megabytes that are also relevant. Multi-channel aids all these workloads by achieving higher scaling. You get both bandwidth and IOPS from additional network interfaces. And it's not just IOPS from the bandwidth, it's IOPS from having another NIC. You can think of the NIC as a coprocessor. And affinity and parallelism in the end nodes by having multiple NICs and multiple slots affinitized to multiple cores gives you that CPU throughput to keep all those IOs in the air. So multi-channel really has several benefits up and down the stack. SMB supports unbuffered I/O. In unbuffered I/O mode, we go zero touch to user buffers. And it uses a strict memory register and invalidate per I/O. A lot of protocols don't do this because it's hard to get performance. But we believe that the integrity, the memory integrity, by closing the window on an I/O, just like a storage adapter does, is key to the integrity of the data. You can't allow a buggy client to write twice or a buggy server to read or write twice. You have to close that window, force it shut before you process the data. And we do that for every I/O. We maintain that performance with remote invalidate and very careful local behaviors such as interrupt moderation. Other SMB uses, it functions as a transport in Windows. You can use it for RPC and you can use it for Hyper-V live migration. I'll give you a performance example of virtual machine live migration in a memory-to-memory image transfer. For bulk transfer with live migration, it's like ultimate throughput. It's memory to memory, so we consider it unconstrained by disk physics, right? Most storage workloads are governed in some way by a moving arm or the speed of the head or the speed of the flash or the speed of the interface or the number of devices, et cetera, et cetera. This is just memory to memory. It goes as fast as it goes. So we have storage quality of service and some other things to maintain it. But we have incredibly low CPU, and in Hyper-V, that's very important to support live migration because we support live migration, which allows us to manage, to run the virtual machine while we're transferring it. So I'll give you 3 examples to close up the SMB Direct examples. The first is a thing that we did approximately 1 year ago, and it's both an IOPS and a bandwidth demo. We use real storage. We use a thing called an EchoStreams Flash SAN 2, which is basically a sort of a white box server with a SAS backend and 6 JBODs, all filled with SSDs. We use Windows storage spaces and 3 multi-channel IB FDR NICs. We use 3 for a very interesting reason, and I'll show it to you in a minute. But anyway, to real disk, to these real SSDs, we managed 600,000 IOPS with this thing. There was a client, fairly generic client, and this flash SAN server. So these are our 8K IOPS. A lot of people are doing 4K, and we're actually moving to standardize on 4K. But 8K is also interesting because it's the typical cluster size of a lot of file systems. 600,000 IOPS, pretty interesting. We do that same workload from cache, and it pops up to 1 million. So actually, these SSDs were not capable of sourcing the full IOPS. If we had more, or we managed things a little differently on the hardware side, we might be able to get more. But we intentionally did a real-world workload. And then we went to a bandwidth workload in which we went to large reads. And it turns out we only had to go to 32 kilobyte reads to attain a throughput of 16 gigabytes per second. 16 gigabytes per second, basically each one of these NICs is worth about 5-point-something gigabytes. So we maxed out all 3 NICs. We were running about 65%, nowhere near 100% CPU on the server. And interestingly, if we went to larger I/O, we got similar results, slightly less CPU, but the same bandwidth, because we were effectively wire limited. You might say, why didn't we put in a 4th? Well, it turns out that the QPI interconnect in the server is maxed out at about 16 gigabytes. So we put in a 4th and we don't go any faster. We've actually maxed out the motherboard of the server. Second one is an in-cast performance thing. It's all very well and good to have one client to one server, but that's not very real world. So here we had a single client reading data from 8 servers. And we raised the thread count and measured both latency and IOPS as it went up. And it maxes out somewhere around 500,000 IOPS. Once again, these are 8 kilobyte IOPS. Maxes out around that much with a very flat latency curve. You can see that it's not breathing hard until it basically runs out of bandwidth. So we hit near line rate with small I/O with a very, very flat latency variance using the protocol. We have a similar result for large I/Os and a little thing for log write at the end, but I'll just gloss over those in the interest of time. Third one is VM live migration. Oh, that second one, by the way, was 40 gigabit iWarp. These were Chelsea cards. The configuration is down in the backup. So this was InfiniBand. This was iWarp. And now we're going to do 2 times 10 gigabit ROCE to show a VM live migration performance. And this one was interesting to show the difference between TCP/IP with compression and then RDMA. And the interesting thing to see is this blue line, which is the actual bytes being transferred. And you can see in TCP/IP it's very limited. It doesn't hit wire rate because we're basically core limited. The TCP stack is highly affinitized to a small number of cores, and you run out of CPU. Even though you haven't maxed 100% of the parallel system, you've maxed out each core. So it takes quite a long time, a little over 60 seconds to transfer the memory image. With compression, you can see that the blue line is way down here on the floor. We're not transferring a lot of data, but we're using a ton of CPU to compress it. And it's still fairly wide. As a result, we're using about 15 seconds of total transfer time. With RDMA, we're using almost no CPU, and the transfer rate basically heads for the heavens, hits the max, and you can see it's just a little line at the top and disappears. And it manages to transfer in under 10 seconds. Interestingly, most of that transfer time is this little tail at the end, which is Hyper-V getting the machine ready to run on the new machine. It takes about 7 seconds once you've live migrated to actually get the machine running. So we were pretty happy with these results in SMB. Second major area, I'm just going to keep going here so in the interest of time because we started a little late and I don't want to delay the meeting. The second area is Windows networking. I have just one slide here and another slide later. This slide was presented at the Barcelona the Europe TechEd event last fall. And it's easy to miss. It's buried at minute 40 of this particular thing. This is a full demo and presentation. But in here, it talks about a new feature for Windows to support a converged fabric, supporting a virtualized tenant, that is, a guest, and RDMA-enabled disaggregated storage traffic with QoS guarantees. It's integrated with Windows software-defined networking vSwitch, and it supports teaming of NICs. Teaming is not something that's supported in the current version of Windows, but will be supported in the future. Well, teaming is supported, but RDMA interaction and guests with teaming are not. So I'd encourage you to go see this demo because it's a major increase in the functionality of Windows networking with offloads such as RDMA. A third major area to talk about in terms of products and services in this case is Windows Azure. So Azure is a worldwide global cloud service that Microsoft provides and sells. This might be slightly old, but it's certainly at least this many. 25 data centers, 1 billion customers, 20 million businesses, and 76 markets worldwide. These little spots on the map are basically some of the approximate locations of Azure data centers. More are being deployed every day. I stole these slides from a presentation late last year, just a few months ago, from Azure. And I want to focus on just one little piece of it. There's an Azure scenario to bring your own virtual network to the cloud, to basically do enterprise hosting, where you take an enterprise, a set of enterprise virtual machines, you bring them into the cloud, you provide them with a virtual network that allows them to communicate as if they were in their data center. And basically, bring as many customers as we can, right? As many as Azure can hold, which is to say virtually infinite because Azure continues to scale. So the challenge is, how does we scale these virtual networks across millions of servers? And hosts-based software-defined networking solves it, and Albert's presentation went into a lot more of the virtual, the host SDN features and virtual networks. But there are two features in particular that are key to it. The scaling the flow of processing to millions of nodes is key. And flow tables on the host and in the NIC with on-demand rule dissemination and RDMA to storage. And Azure is deploying both these things, and I'll just give you a quick thing. You can see a demo if you bing express route to the cloud. This is from Albert's mail. Flow tables are a little bit off topic perhaps for this, but I just want to whet your appetite with them. The Azure VM switch, this big orange box in here, is a software component inside one of the nodes that's hosting one of these enterprise virtual machine applications. So the vSwitch, or the VM switch, exposes a typed match action table API to the controller. The controller is up here in Azure. The controller needs to tell the switch exactly what to do with each packet, including encapsulation and decapsulation, rather than trying to use the sort of per machine and per flow abstractions. And so it does that by taking a VNet description, a virtual network description, to instantiate a routing policy. And the routing policy basically encapsulates packets, right, and tells the switch where to send, what NIC and what destination to send it to. But more than that, a tenant description also controls two other very important things. ACLs, basically a firewall rule, and NAT endpoints, this load balancing NAT. And so this provides firewalling, this provides address rewriting, and and this provides for encapsulation for routing through the Azure cloud. And so just think about this in the future, but it's a very compelling Azure feature. However, let's say we have this, a complete virtual network. We need storage as well as compute, right? Those are the two main functions that cloud virtualization needs to provide. So how do we make Azure storage scale? Well, Azure storage becomes software defined as well, It wants to make storage clusters scale cheaply on commodity servers. Erasure coding, you can read all about this, but it's a durability of 3 copy writes with a fairly small overhead. But erasure coding has a very important property. It requires an amplified number of network IOs for each storage IO. So you can see a write come in, and the write has to be committed to 3 other nodes, right, before it can be acknowledged. Otherwise, it hasn't been properly stored by the cloud. Well, guess what? Right? There's a little explosion of writes that happen within those guys. So RDMA, high performance transfer storage. I don't have to tell you how the first thing goes, but I want you to focus on a couple of things. RDMA primitives, zero CPU utilization to 40 gigabits. ROCE v2 enables InfiniBand transport over a routed IP Ethernet network. And so Azure is seriously in the process of considering and deploying ROCE v2. We talked about this previously. So it's being enabled at 40 gigabits for Windows Azure storage. And the goal is massive cost of goods savings by eliminating many, many, many CPUs in the rack. So this allows Azure to meet its cost goals and scale.
Does this use case for Azure use SMB?
SMB is available in Azure, but this particular use case does not. Software interfaces, the final leg of this. Azure RDMA software. So you may have heard about Microsoft HPC Server previously. That is migrated to the cloud, right? We now do Azure. Azure does HPC, so we provide HPC in the cloud. And there are 3 basic things that I want to just mention today. The first is, in case you're not familiar with it, Network Direct. It's a Microsoft API. It's a set of defined programming interfaces for RDMA. Transparently supports, guess what, all 3 major RDMA. And guess what, IP addressing based. It's designed for Windows. It's a native Windows API, right? Network Direct. It's called the NDKPI. It's designed for Windows, high level of abstraction, fabric agnostic, stale ABI, the ABI as well as the API is stable. It doesn't do callbacks. It uses waiting for events and the like. Provides for dynamic discovery of providers. It's extensible, all singing, all dancing. Network Direct has been out for quite a few years, and it's in. There's been several updates to it. But there's a new thing that was added about a year ago, I think, called Endure. It stands for Enlightened Network Direct on Azure. It's kind of a corny name. But it's a virtualization layer for RDMA. It enables full bypass with 0 overhead to the VM, targeting Azure-supported RDMA fabrics. It's actually in production on Azure today. You can get you can buy time on an Azure machine that supports this Endure. Scalable to thousands of cores. I think we've run it up to about 2,000 right now for real-world applications. And it's now supporting Intel MPI as an API on top of it. Future supporting the Linux guest, and that's where I'm about to go in the presentation. But first, just a quick picture of Endure. It might be a little bit of an eye chart because I had to steal another presentation. But you can see the host OS running here as, if you will, the control application, and guest virtual machines also running on that same hypervisor. And some guest virtual machines will communicate with the host OS, and some of them can run standalone. But they all go to the RDMA hardware, and you can see that they all have this direct line dropping down. There's a virtual device driver that captures the, if you will, privileged operations, but it enables direct access to the hardware for the hot path operations. So you can expect full performance from this for all the interesting operations and receive, hardware-specific work queue operations. And the final slide I want to bring up.
Does that Endure support virtual functions in VMs?
That is a Windows platform question that I'm going to have to leave hanging today. Linux guest RDMA on Azure is the last piece. This is a in-development project. My colleague KY Srinivasan, who's been a prolific contributor to Linux for other virtualization functions, is in charge of this. It is based on network direct technology. It uses, if you will, the network direct plumbing and API machine. It puts all control plane operations over the VM bus, just like the Endure service does for network direct. So connection, establishment, teardown, creation, and management of all these privileged resources happen over the VM bus. That's this little guy right here, where it talks to the host OS for permission, if you will. Data plane operations, however, bypass the guest and host kernels, just like the native network direct on Endure. So the data plane goes straight to the hardware. The RDMA NIC directly operates on pinned application memory, so it's registered memory is pinned. And a new Linux driver up in the Linux guest bridges the gap between the Linux programming model and the Windows network direct programming model. But there's no change to the Linux user level environment above that. So if you will, there's a paravirtualized driver in Linux that's aware of this same network direct and Endure framework. And that's in development, and you can expect.
What API is the Linux guest?
It presents a verbs API. It's just another adapter, basically. Not DAPL,
No,
verbs.
It's just a verbs provider.
Yeah.
Is there an intention to hopefully do an LFI provider?
I can't speak to that. And that's it. Oh, there's one more. There's the NDKPI. I threw this at the end. There's another version of Network Direct in the kernel. This is used by SMB Direct. Might be used by others in the future. There are 3 different versions. And there's an NDKPI reference online in the resources below if you're interested in it. You could write device drivers for Windows that would access RDMA using this tool. Thanks for holding most of the questions, and I'll be happy to take more of them. In the back, Chuck?
I'm just wondering if your Linux virtualization allows guest-to-guest communication without hardware HCA involved?
Does the Linux virtual communication allow guest-to-guest without a hardware HCA involved? No. First of all, guest-to-guest is one of the topics that I can't really talk about too much right now. And second, we have no plans to make a virtual RDMA adapter right now, at least not that I'm aware of. It's an interesting idea. Another question in front of Chuck? Yeah.
The VM migration, is that user space or kernel space?
Is the VM migration user or kernel space? It's handled by SMB, so it is initiated in user space by the Hyper-V host, and it's executed by the kernel SMB provider. So the data transfer is kernel space, but initiated from Hyper-V. Basically, it opens the remote memory image as a file and writes it.
But it's a memory-to-memory match, right?
It opens a memory image as a file and writes it. So you read memory with loads and stores, and you write it with SMB, and it's placed on the remote node. So I'm sorry, but it drops from the Hyper-V host via a write file API to appear in memory on the remote node. Other questions?